Orogenic wedges make a great model for small orogenic belts like the Alps or New Zealand, Taiwan, Pyrenees, places like this. But what about the big orogenic belts, particularly the ones that have large orogenic plateaus like Tibet on the right or the Altiplano of the Andes here on the left? These are large regions with very thick crust over hundreds or thousands of square kilometers. How is it that these sort of fit into this view of an orogenic belt as forming a crustal wedge being driven by subduction? Well, in fact, if one looks at one of these systems in detail, parts of it do look very much like an orogenic wedge. And in particular, if one goes to the peripheral regions, for example, here to the south of the Tibetan Plateau, this is a seismic cross-section or a cross-section based on seismic data in any case that crosses the Himalaya from the stable Indian continent, across the Lesser and High Himalaya up into the Tethyan Himalaya, and finally the Tibetan Plateau. And what you can see is that there is a subduction-like process going on underneath the Himalaya. There's underthrusting of India. There is a detachment. These are earthquakes mapped along here. So there appears to be a detachment between a deforming zone and an undeforming zone. But this is sort of limited to the edge of the mountain belt. And as the crust thickens, we start to lose this sort of wedge character. However, the deformation is still largely consistent with this sort of a model. Now, this is the same, more or less the same section going from India up into Tibet. This is the high part of the Tibetan Plateau. In this peripheral region that is underlying the Himalaya, we see these thrusts that are coming in here. This is the main frontal thrust, the main central thrust, and so on. This is a fold and thrust belt with large stacking of naps and so on. This could look like a little Alps if you'd like in here. Where it's different is then we move into the interior, the plateau part of the system. We still see evidence for deformation through this region, but the crust is now very, very thick. There are fewer earthquakes. It's harder to identify active thrusts. The whole sort of nature of the deformation has changed. And we can see also in the seismic data that there is a change in at least the material properties of the crust that's underlying the Tibetan Plateau. So again, here's our wedge part of the system out here. But as we come into the plateau, we see things like in the seismic velocity, this is the seismic velocity structure up here. We see a low velocity zone that is in this region, the upper crust. It's a relatively low velocity compared to regions above or below. And this kind of low velocity is typically associated with at least small degrees of partial melt of the crust. And that's what is interpreted in this lower diagram here, that the mid to lower crust, maybe above a mafic lowermost crust, is potentially partially molten. Now, what does that mean mechanically? Well, mechanically then, we have our underthrusting and our wedge being formed out here, but as this Indian crust becomes deeper and deeper, the detachment is going to shift from brittle to a ductile deformation as the temperature goes up. And in fact, here the temperature must be going up enormously because of this partial melting that's evident in here. And so the detachment and the wedge itself are both going to become very, very weak. And in particular, if you think of the detachment as going to essentially zero strength as it moves down underneath this partially molten region, we could actually think of this region as being a critical wedge, but one in which the lower detachment is both viscous and very, very weak. And a very, very weak detachment means that the upper surface slope is going to drop to something very, very flat. And that, in fact, is one way of interpreting this orogenic plateau. It's a flat wedge with essentially no taper angle, and it's flat because this is a very, very weak material underneath. Now, there are other implications of this that are sort of related to the wedge dynamics, but not so much. But one of the, at least in part, but one of the implications for having this very weak lower crust is that this partially molten material is going to begin to squeeze out laterally from underneath the high plateau. And this has implications then for the wedge dynamics out here in the Himalaya, for example. So again, these are the thrusts of the Himalaya. But in particular, there's a very funny occurrence, a structural occurrence out here in that there is or was at least an active normal fault in this system in say the mid-tertiary kind of Miocene times, early Miocene. There was actually a big normal fault that was active in here. And this gave this rather funny kinematic pattern to the Himalaya, where all of this region was in fact being extruded out to the surface, and in fact being removed by erosion to a large degree. But in fact, the region behind this big normal fault was largely undeformed. And we have sediments that are preserved up here. We have it's showing these nice domes, but in fact, there is this was largely undeformed or undeforming at the time that this was active. And so this partially molten zone sort of permitted the lateral extrusion of much of the mid-crustal levels in here. And this is shown sort of by these arrows here. This part is moving faster than the material underneath the normal fault. So in fact, this is an example where we had an active thrust fault and an active normal fault, one above each other, and these are active at the same time. So this certainly doesn't fit our ideas of having an extensional regime or a contractional regime. It's something quite different, and it's being driven by this push from behind. So this is, again, just a model of this sort of process. A little bit fuzzy. My image didn't come out very well, but it's showing that as this, if we go through time, as the crust begins to heat up. By the way, why does it heat up? Why would this be hot? Well, this is probably mostly because we're thickening the crust, and we're thickening the crust by accreting material in the front, the Himalaya here. That accreted material is upper crustal material, and upper crustal material has relatively high concentrations of uranium, thorium, and potassium. These are the radioactive or the heat producing elements in the Earth. So we're essentially adding heat producers into the crust through this accretionary process that's occurring here. As those radioactive elements begin to generate more heat, that's going to heat the crust, and we end up with very high temperatures in the lower crust. With time, it gets hotter and hotter, and we see then this sort of extrusion process beginning to occur as this material gets squeezed out to be exposed in the Himalaya region. Shortening, however, continues across the entire Himalaya. In spite of this sort of focus on the high Himalaya, you can in fact see that there is this is elevation shown in gray, but all of these points are in fact the velocity across in a north-south direction or in an east-west direction, or the green lines. So you can see that there is in fact some I got that backwards. This is along the profile that's running north-south, and across the profile is the orange points. So there is a velocity gradient from high velocity of India down to low velocity in Central Asia. And we also have some lateral motion material in and out of the plane. So, but that deformation, that's showing that this deformation, in fact, is extending all the way across Southern Asia for several thousand kilometers. The Andes is a similar story. This is a very crude cross-section of the Andes, but it's showing what the total crustal thickness is and the total elevation for a west to east profile across the main Andes. That's showing the Western Cordillera, Altiplano, Eastern Cordillera, and the Subandean belt. The crust is very thick again underneath this high plateau, but these have kind of a taper to them, right? There's a slope as we come down out of the plateau. And if we look at the structures, I'm not showing a very good structural cross-section of the Andes here, but here's a very idealized picture of this. We, in fact, have subduction going on under here. We have a detachment. We have accretion of material, not very much. In fact, there's probably more material eroded away than accreted, but there is deformation of this front and the formation of a little critical wedge, if you'd like, in here. Probably more interesting is if we jump over to the eastern side, then we also have underthrusting. Now, this is not true subduction, but what we have is motion of the South American plate towards the trench. And that means that this is moving in this direction towards the slab. But as it moves, it again has a detachment to separate an upper plate from a lower plate. That detachment then is the material above the detachment is deformed by crustal accretion, and we have a little critical wedge sitting in here. Here's our alpha and beta again, showing that we in fact have a deformed accretionary wedge or orogenic wedge on the side. So again, much like in Tibet, you could think of this as being wedges on both sides, and then probably a hot lower crust, flat plateau, undeforming region which forms the altiplano stuck between these two accretionary wedges. Now, one of the problems with the Andes is that we have almost a double subduction situation here. We have underthrusting on both sides, and that creates a space problem. Where do you put, if you really start to underthrust a lot of material from South America, what's going to happen to this? Where's that material going to go? And there are various arguments for this that are arguing, particularly depending on what the dip of the other slab is, whether or not material really gets crammed in here, whether or not it gets pulled down or it detaches. For example, if it's a thick eclogitic root to the crust, as has been argued here, that is gravitationally unstable, and it may break off and go down, either down the subduction zone or simply fall off or drip off of the bottom of the lithosphere like this. But somehow one has to get rid of this excess material as it comes underneath. And it's been argued this could happen episodically through this kind of a process, or continuously from some kind of a cyclic flow through here.